So we've got our value for g, but we need to know what the uncertainty in that value is. Okay, so my plotted points looked like this. I had a line of best fit. If you've got large error bars, that can make this process a little bit easier, but you probably won't have that. So what you've got to do is draw another line of best fit. The sort of most extreme line of best fit you could get away with, not that. It's going to be quite close to the original if there's not much scatter on the graph. The more scatter is, the more wiggle room there could be. I've drawn a maximum. You could draw a minimum. This is going to give me a larger gradient. So the original gave me gradient m. My maximum line is going to give me a gradient m max. And what I do is I work out another value for g in the same way. So remember, g is pi squared over m squared. This is going to give me, in my example, g min. If you used a minimum line, it would give you g max. It doesn't really matter. So let's just say, for sake of example, e.g. g equaled 9.5. Let's say I do this process and I get a g min of 9.1. My answer is a combination of those two things. So my answer is, of course, g equals 9.5. But I want the difference between these two. It gives me my uncertainty. Plus or minus, in this case, 0.4. Brackets and the unit, meters per second squared. So it's quite an easy process to get this final bit. And you can even do it without error bars if you haven't calculated them, but it's better to have everything and not lose out on any of the marks. But don't feel you can't do this bit if you haven't quite got your head around error bars. Or if they're too small to show up, you can still do this. There just won't be much variation. Make sure whenever you give your answer, you quote it in full like this. An answer of g equals 9.5 meters per second squared is not an answer. Unless it's got the uncertainty with it, it's no use. So make sure you always quote the answer with its uncertainty.